Hi everyone, and welcome back to another lecture of pre-calculus. So we are almost at the end of the topics that we wanted to discuss because we already talked about sets. The most important thing that we need to do before diving into calculus is functions, because that's all that we're going to deal with when we're doing calculus. So from today's video and maybe two videos more, we'll just talk about all these things that you can see on the screen. That is, we are going to talk about relations and functions. And as you can see, the content is organized in the following way. First, we talk about something called a mapping. We will define it, what mapping is. And through that, we will talk about ordered pairs, relations, and then we'll define functions, different operations on it. And after that, we will talk about domain and range. And finally, we'll talk about graphs and plots. And the reason I marked trigonometry with a star is because maybe I'll talk about it, but this will be a really brief talk about trigonometry because I'm assuming people who are watching this have already been through all of this stuff. They're just taking it for a refresher. And let me know, like, trigonometry for us, from the point of view of calculus, like if you're not doing coordinate geometry, um, there will be some just functions, some periodic functions, and we'll just need some of the properties to do calculus. But yeah, if you really want to dive into trigonometry, maybe I can make some more videos about that. So if you want that, let me know down in the comment box. Okay, so yeah, that's pretty much it. That's pretty much the plan before we jump into calculus. So let's start by talking about something called a mapping. So what is a mapping? So far we have encountered sets and some operations on it. So let's say, you have some set called 1, 2, 5. And let's say you have another set B, which I'm calling as, -1, -2, -6. Now, what if I can produce a machine, I can build a machine like this. This is my machine M, which takes input from set A. That is, it will take input as 1, 2, 5 as its input, and in the output, it will give some element of B or all elements of B. So -1, -2, -6. So this machine is consuming the elements of set A and producing elements of set B. In this sense, mathematically, we will call M in general a mapping. From set A to set B. Or you can say this is a mapping from elements of set A to elements of set B. Now, people who have already have gone through these stuffs, they might say this is the definition of a function, but I assure you this is not. Function is a special sort of mapping, and in general, all these mappings are called relations and stuff. So function is a special kind of a mapping, and we will see why that is the case very soon. Similarly, okay, so let me just write this down mathematically in a more fancy way. So M is, this thing, like the thing that I wrote over here in words, can be written as this as well. So this just reads the fact that M is a map that takes input A and spits out input B. In this case, these are sets. They can be anything. Your A can be orange, and if M is a blender, you know, and from orange you get some orange juice and stuff like that. If it's a meat grinder, you put in some meat, and then you get, your lean meat or sausages and whatever. So yeah, so these are all mappings, okay? Now, there is some sort of a map that takes elements of set A to elements of set B. Let's say for this example, 1 gets mapped to -1. Since this is my set A consists of 1, 2, and 5, and my set B consists of -1, -2, and -6. Similarly, 2 gets mapped to -2, and 5 gets mapped to -6, right? Yeah. So we can just, draw some diagrams just like set theory to represent this. So this is your set A, this is your set B, this is some mapping M, this is 1, 2, 5, -1, -2, -6, and this is how the mapping looks. Okay, what we can do is that we can write this, a more organized way, not referring to diagrams and stuff, because you have, let's say you have many elements, so the diagram would be longer, and let's say you are a lazy person like me, you don't want to write that. So what you do, you find a new way to write it. So let's say I will now define something called an ordered pair, but let me just work out this example first, like how I want to write it. So let's invent a new way to write this mapping. So 1, we can read off this diagram as 1 will correspond to -1, 2 will correspond to, like when I say correspond to, like input 2 corresponds to output -2, and so on. So what if I write this whole correspondence into a set? Let's call that set as C. So 1 is corresponding to -1. Note the specific order that I'm maintaining over here is that the first element is the input, that is this guy, input, and the second element is the output. Similarly, I can write 2 minus 2. Again, this is the input, this is the output. And lastly, I can write 5, comma -6, and then I can close the second bracket or the curly braces. So this is a new way to write what that map was doing from set A to set B, right? And now we can define something called an ordered pair. Each of these pairs that are closed by parentheses are called ordered pairs. So in an ordered pair, you have two elements that have some specific mapping in between them. I mean, that's not the most rigorous mathematical definition out there, but since we are doing pre-calculus, that will suffice for us. However, if you are someone who's into pure mathematics, you want to do like rigorous mathematics, there are books on set theories that discuss more about disordered pairs, and they have more rigorous definition for it. Our job here is to just get an intuitive idea for ordered pairs so that we can do our calculus thing in a smooth manner. All right. So as I was saying, these pairs are called ordered pairs where the first input consists of the elements of set A, the input set, and the second element in these pairs is coming out of the output set. So this is our ordered pair. In general, what can happen is that, let's say you have some element X belongs to set A and Y belongs to set B, and there is some sort of a mapping F such that it A So as I was saying, let's say there is a set who has the element of x. We are calling some element x as a general thing. It can be any number, it can be anything else. So if x belongs to A and y belongs to B, where A and B are both sets, and you can define a specific map if is such that it takes something from A and maps it to B, then the ordered pairs, let me just do a little bit something. It's called indexing, xi, so that you can distinguish in between the elements. Or if you're just comfortable using x and y, you can just ignore this notation. It's just a matter of notation, nothing else. Then the ordered pair under this mapping is, let's say the ordered pair will construct a set C. It will have all the elements like x1, y1, x2, y2. I is an index that can run from 1 to infinity and whatever, and so on. I'll just write xi, yi. So these are all your ordered pairs, okay? So in short, the ordered pairs are something where the first input or the first element acts as the input and the second element acts as the output. That's the most non-rigorous way of saying it, I guess. I mean, that's what I understand, from the most non-rigorous point of view. So these are your ordered pairs. So let's say now let's take a look at one example. Let's say I give you a diagram like this. Let's say this is A, this is B, this is some F. We don't necessarily have to mention it F. And let's say I say A has some elements 11, 2, 3, 5. And let's say this is 6, 7, 8, 9. And let's say 11 maps to 7 under this mapping. 2 goes to 6, 3 goes to 8, 5 goes to 9. So, and then I ask you to construct a set of ordered pairs. So how do you construct the set? It's pretty simple. You just take the input, take the input 11, the first element of set A, and see where the mapping takes it to. It takes it to 7. So now you have 7 over here. Similarly, you can write 2, and when you input 2 into the map will tell you 6. Similarly, you can go for the other elements as well. 3 goes to 8, as you can see from the diagram, and then 5 goes to 9. Conversely, if this set is given to you, you can just draw this diagram as well. So this thing goes both ways. Now, let's consider another example. Let's say 1, 2, 3, and you have only one element over here. And let's say the element is 11. I'll say 1 goes to 11 and 2 goes to 11. However, there is no mention of what happens. So in this case, you can ask this question, right? Can we form an ordered pair? At first, we can write something like this. 1, 11, 2, 11. It's entirely possible that two of the inputs will give you the same output. It's absolutely possible. However, when you want to find the last pair, you see, even though you have some input, let's say your map is not showing you any sort of an output. Okay, so in that case, can you construct an ordered pair using all of these elements from set A? And the answer is no, because there is no output, right? The map doesn't lead you anywhere. It's like You are looking at the world map and there is some sort of a end of the world or something like that. So in this sense, if you do want to construct an ordered pair, you have to restrict yourself within these two numbers, 1 and 2. You cannot take 3 into an account. If you do take 3, then you won't be able to map all the elements of set A to all the elements of set B. That is, you cannot map all the inputs to all the outputs. You can't trace it. And we'll see where this sort of concepts are useful.